Okay, Unit 7 practice test, here we go. So this is going to be electricity and magnetism test. So we rub a balloon on your head. The balloon gains a charge of negative 0.05 coulombs. What is the charge of your head? So before you rub them together, your head's neutral, so 0 coulombs. The balloon's neutral. After you charge them together, well, we know that the balloon is going to be negative 0.05 coulombs. Now, here's the thing. Charge is always conserved. So what that means is the total charge here is equal to the total charge after. So 0 plus 0 is 0. That means your head has to have a charge of plus 0.5 coulombs in order for charge to be conserved. So, since both were equal before, you have to be able to add them up and get an equal charge after. Now, the reason why this is happening is because the electrons are moving. So the electrons move from your head into the balloon, or rather onto the balloon. How is charge being conserved? The total charge is constant. Just like everything else that's been conserved. Energy, total energy is constant. Momentum, total momentum is constant. Mass, in a couple units, is constant. Okay, number 2 down here. The metal spheres are touched together. What is the charge on each sphere after they touch? So, when these two touch together, the first thing that's going to happen is positive and negative attract each other, right? So, we're basically going to get rid of these positives. They're going to go away. And 2 of these negatives are going to go away. So that leaves 4 negative charges. Now, 4 negative charges aren't just going to hang out all in one place. Negatives repel each other. So those negative charges are going to push each other around until they're basically divided up between the 2 spheres. These metal spheres are always going to be identical. The reason for that is identical ones are going to carry the same amount of charge. If one was larger, it would have a little bit more charge than the other one. But we don't have to worry about that because they're always going to be identical for us. Draw the electric field around these objects. So the electric field is the area around the object where another charge is going to feel the force. We draw electric fields to show which way positive charges would feel a force at that point. Those are the easiest ones to draw. But you're not going to get any credit if you just draw that on the test. So, what's going to happen to a positive charge in between here? Well, it's going to get pushed either up or down because these electric fields, they can't cross each other. So they're going to go like that. And the reason why they can't cross each other is because if you think about it, if they're crossing each other, that means that at that point, the charge would get like a force in one of 2 different directions. Like, that's not sensible. So, charges, you could balance a charge right in the middle here because the electric field is so weak in between these. And we figure out how weak the electric field is by looking at how closely spaced the lines are together. So the closer they are, closer together. Or the closer together they are, the closer together they are. Oh my goodness. We'll cut that out in post-production. The closer they are together, the stronger the electric field is. Okay. Draw the following circuits, a series circuit. So first off, every circuit needs to have a voltage source. For us, those voltage sources are going to be batteries. Now, series circuit just has one path. parallel circuit has a path for each thing that is connected to it. So if there's 3 light bulbs, there's going to be 3 paths. So series circuit is just going to go like 1, 2, 3. Now it doesn't matter. You could put all 3 up here. You could put all 3 over here. Really, just to be considered a series circuit, you've just got that one path for electricity to flow. As long as there's no breaks or any forks in the path, you've got a series circuit, no matter how you place these around. In a parallel circuit, you need to have one path for each one, so that's going to branch off and go just like this. Now, is your house wired in series or parallel? I would almost love it if you could prove to me that your house was wired in series, because there would be no reason not to wire it in parallel. If your house is wired in series, that means that you would have to have all the lights on or none of the lights on. They'd all be connected on the same circuit. Whereas in parallel, you can turn on the lights in just one room, right? So your house is going to be wired in parallel because you have multiple places. And like you can turn on the lights in just the dining room. How does a fuse protect a circuit? Oh my, I needed a fuse to protect the circuit just yesterday when I blew a fuse. So this is a fuse. Basically what it is it's a very thin piece of wire. If you take a look, it's written on here, the rating. Oh, except I should probably get it in focus. So, and then the lights go out. And the lights always go out. Okay, so this one says 250 volts at 0.75 amps. So that means that if I go above that, this fuse is going to break. So, how does the fuse protect the circuit? The fuse breaks. Before the circuit is harmed. Honestly, it does break. By breaking the wire inside, which creates an open circuit. Okay. On the other side, so on the other side, we're talking about Ohm's law. So on this sheet, I wrote Ohm's law a little bit different than I wrote in the notes. So here I wrote V is equal to IR. We should be able to solve that for I is equal to V over R. We can write Ohm's law a couple different ways, right? V equals IR, I is equal to V over R, or R is equal to V over I. I'm just using algebra to rearrange those equations. So if a light bulb has a resistance, so resistance is R of 250 ohms, is my poorly drawn omega, and is connected to a car battery, which is 24 volts, how much current will flow through it? So current is just V over R. So 24 divided by 250 gets me chance to pull up my phone. You should just fast forward until I get the answer. Or take the time yourself and get the answer. So I get a current of 0. Oh, hey. Got a text from my sister. Oh. one more thing to cut out in post that I won't actually. Okay, how much power is used by the light bulb? So power is I times V. So that's going to be 0.096 times my voltage. And I get 2.304 watts. It's power. We were introduced to power way back in Unit 4, and it's been watts ever since then. So this light bulb would be rated a 2.3 watt light bulb. Person who touches the third rail on the train track at a voltage of 750 volts is going to have a bad day when 0.09375 amps of current runs through them. The person's resistance would be, now here's the thing, a person we're going to expect to have a rather large resistance because electricity doesn't flow through people easily. That's why I don't just pay a bunch of people to act as my circuit in my house. Could have them all hold hands and connect them up to a battery. But people aren't great at that. And mainly we're complainers. So 750 divided by 0.09375 gets me 800 ohms. Okay, what is the difference between static electricity? So anything that's static means still. So static electricity is unmoving charges. DC current. So DC current stands for direct current. So direct current is going to be charges moving at a steady pace. They'll move in the same direction at the same speed all the time. An AC current is when the current fluctuates. So current, and by current I mean moving charges. Back and forth. So DC current comes from batteries, AC current comes from generators. So in generators, as the magnet spins, the current's going to go one way and then reverse and go the other way. 3 ways to make a magnet. We can find one naturally. So you head out in the woods, you find yourself, why do I keep saying woods? You head out somewhere where there's rocks. You're going to find yourself some magnetite, if you're lucky. Once again, first people who found magnets were just digging with iron shovels, and they were like, hey, why is these little flecks of rock sticking to our shovels? 2 is electromagnetism. So with an electromagnet, you're going to want to take a coil of wire, run electricity through it, and you'll make it a magnet. And then number 3 is induction. So that's where we take a piece of magnetic material that has several different domains. And these magnetic domains are just places in the material where all the atoms point in the same direction. If you apply a strong enough magnetic field, that same piece of metal, you get all the atoms lining up in the same direction. So you get one big domain, and then you're good. You've magnetized that material. To draw these magnetic field lines, magnetic field lines around the magnet. Unlike around charges, magnetic field lines do not necessarily start perpendicular to the object. They can, but they don't need to. And you're going to get something that looks like a clam or a butterfly. I used to say butterfly, but people used to say it doesn't look like a butterfly. But I think it does. There we go. Look at these antennae on my butterfly. And these, whatever the opposite of antenna are. The very last one, describe how a generator produces energy or electricity. Well, a generator has some outside force. That's what the crank here is for. That turns a magnet inside a coil of wire. So this magnet here has some sort of magnetic field of its own, right? As you turn it around and around and around, that magnetic field is going to be changing. So the changing magnetic field is going to create a current in the coil. Okay, how do we do? 17 minutes? Well, that flew by, even with the lights going off.